So in this lecture we are going to discuss about mappings and stereographic projection. So in our last lecture we learned about functions of complex variable. Let's say you have some complex variable z or a complex number z, and you can assign this z to some machine that spits out some f of z, right? So this is our functions of complex variable, and this is in fact in a sense called a mapping. That is, you are taking some collection of points or numbers and you are mapping them with some machine that takes points from here and it generates some output. So this is a mapping. And in a single variable calculus, this is pretty easy to see. You write y equals to f of x, right? And you can draw a graph like this, whatever that may be. So in single variable calculus, this is pretty simple because you only have two variables and you can plot them in a single graph. However, when you do this complex variable, you can see that this z is actually carrying x and y inside it, and f of z is also carrying x and y inside it. So essentially you have like four variables. So that's why you need two planes. One of them is called the z plane. So you can think of this as the plane that displays all the inputs that you want to give. This is the real axis, this is the imaginary axis. I'm also labeling x and y. And then through the function there is another plane. As usual, it's called a w plane, where w is defined as f of z, or you can also call it the image of this plane that is getting mapped. So again, this is the real axis and this would be the imaginary axis. So how can we see this mapping? Let's say a very simple function z square, right? So we want to see what happens if we take all the points in the upper half plane of z. That means all the points over here. We are not considering the lower half, only the upper half plane, where the imaginary part would be greater than 0, or so to say y greater than 0. Okay, we want to see how these things get mapped when it's put through this function z square. That means how this z square takes points from the z plane and how it maps to the w plane. That's the thing we want to see. So let's begin the analysis. So this is our f of z equals to z square. There are two ways you can do it. You can do it in the Cartesian way, you can do it in the polar way. I'm going to stick with the polar form because that's more convenient and that's pretty easy to visualize as well. So in the polar form, z is equals to r e to the power I theta, right? And for this upper half plane, this theta is restricted from 0 to pi, right? Because theta can start from here and it can go all the way up to this point. It cannot cross this point because that would violate the condition of this upper half plane and stuff. So this is the restriction on theta, and r can be anything that goes from here because r is a positive thing always, no matter where you take it. Okay, so that's why we're focusing on theta. So what is z square? So f of z square, or let's say you can call it w if you want. You are writing this thing in terms of r e to the power I phi, like this, right? You are calling it like this because this angle over here you want to call it phi and you want to call the modulus as capital R. Okay, now we also see that f of z is defined as what? Z square. This is the form we are assuming, and this is the input that we need to give. That means we give the input z and it spits out z square. So this z square would be just r square, and there would be e to the power 2 I theta. So we have r e to the power I phi is equals to r square e to the power 2 I theta. and from here you can conclude that capital R is equals to R square. This is one part, and phi is equals to 2 theta, right? Now let's focus on the theta part first, and we'll get back to the radius part later. So from here you can solve for theta, and this is just phi by 2, right? And if you put this into this inequality, then what do you get? What you get is that you write this pi theta 0, and instead of theta you store in this phi by 2 0, and you can multiply this thing with 2. That's just a scaling. That should give you this thing, right? So what does this mean? It absolutely doesn't make any sense. Oh, I made a mistake of writing the domains here. Sorry about that. It should be on the reverse order, because yeah, this is less than, theta is greater than pi, but it's less than 0, so that doesn't make any sense. So this writing here is not correct. Sorry about that. It should be 0 theta pi. Yeah. So we have this 0 phi by 2 pi, and finally you have 0 phi and 2 pi. So what does this tell us? This angle thing is that this upper half plane on, let's say this, call this figure 1, and let's call this figure 2, gets mapped under z square mapping into the whole upper half and the lower half plane. What I mean to say is that the upper half plane on the z plane gets mapped into the both upper half and the lower half part, because 0 to twice pi means a full circle like this. So this red region over here would actually be mapped to this whole complex plane, the whole W plane. Okay, that's one thing that we can say from this phi. And what about this capital R is equals to R square? So let's now consider some physical problem. Let's say you have a particle like this. This is the z plane again, and let's say this is the W plane. Okay, and let's say you have a circle on this z plane. We'll move to the particle thing later. And if it has a radius of r, then this circle would get mapped into the W plane with a radius of capital R, which is equals to r squared. So there would be a bigger circle which has a radius of capital R, which is equals to r squared. This is how this whole thing plays out. Now if you consider a particle that is moving in a circular path in the z plane with some angular velocity that is defined as d theta by dt, then this particle in the W plane would, I mean the mapping of this particle, or so to say the image of this particle, would move into a circle of r square, but with a velocity omega prime as 2 omega. Why? Because just look at the relation over here. Phi is equals to 2 theta, so dd of phi by dt is just 2 d theta by dt, and this is omega prime is 2 omega. This is one way to see it, like a physics problem. Okay, and there are many interesting mappings like z square. You can have z bar, you can have z cube, you can have z plus 1 upon z, and so on and so forth. Hopefully we'll see these things in our tutorials and exercises. Now we are sort of done with this mapping thing, but we will be back later to discuss conformal mappings in details. Now the last thing that I want to discuss in this lecture is something called a stereographic projection. Okay, I forgot the spelling. I think it's stereo, right? So this is stereographic projections. So if you have noticed so far that we didn't bother about talking the points at infinities in the complex plane. So now we are going to talk about those things, and we're going to see how we can use these stereographic projections to map them. And this is also pretty interesting when you want to deal with these points at infinities, you want to define limits at infinities, and so on. So the first thing we're going to do is that we're going to draw a complex plane like this, and this complex plane will include the points at infinities as well, and this is also known as the extended complex plane. So the extended complex plane that contain this is something that contains points at infinity that are denoted with, let's say, z infinity or infinity. It is just a matter of convention. So this is our complex plane C. Now let's say this is the origin, that is the intersection of this x and y axis and stuff. Let's say this is x, this is y, minus x. We usually don't show minuses, but whatever, let's show them. Now consider a unit sphere. So unit sphere, which is also known as the Riemann sphere, like this. Okay, the drawing is not pretty good, so I think I need to draw it again. Yeah, let's say something like this. Okay, let me just remove these lines so that you can understand what I'm trying to do. Replace this thing with a dashed line. Okay, so this is our sphere, and let's call the sphere with capital S. And in the sphere we have two poles. Remember that this is the origin, this is the origin, and this origin will be our south pole as well. We'll prove that, but for now this is our south pole. Okay, let's call this, should we call this sphere as S? Okay, let's call this S prime. S prime is the sphere, and this is our south pole, this is the north pole, and this is a unit sphere. That means it has a radius of 1. So since this is the origin and the sphere is a 3D thing, the coordinates of the south pole would be 0, 0, 0, 0, and the coordinates of the north pole would be 0, 0, 2. Okay, now what do we want to do with this sphere? If you notice that we can take any point in the complex plane, and what we can do is that let's take this point, let's call this some z, and we can draw a straight line from the north pole to this point. Let's use a different color, like this, and this line would intersect the surface of the sphere at some point. Let's say this this point, and let's give this a name. This point is called P, and it has a coordinate of capital X, capital Y, capital Z, right? And if you draw this picture properly, or if you just think for a bit, you can easily understand that any point on this complex plane or the extended complex plane can be joined to the north pole that will intersect the surface of the sphere only one only at one place. That means think of it like this. Think of it, this is the sphere, okay, and this is the whole complex plane thing. You can have a point like this that can be joined with the North Pole. Let's say this is the North Pole, let's say this is Z1, like this, and it would puncture the surface at, let's say, point P1. If you have a point over here, let's say this is the surface. Obviously this is a 2D graph, so the drawings would not be pretty good, so on and so forth. So for every point on the complex plane, you get a unique point on the surface of the sphere, and this is achieved via drawing a straight line from the North Pole to the point in the complex plane. So this type of projection, that means taking a point from the complex plane and projecting it on the surface of the Riemann sphere, is known as a stereographic projection. And in fact, from your intuition or from this kind of graphs, let's say this is the point Z infinity, you can see that if you continuously take points like this Z infinity at some point would just correspond to the North Pole, like this. Obviously this is not an appropriate diagram, but we'll show this mathematically. So our next goal is to relate the coordinates of these 2 points. That means if you have a point, okay, let me just write our goal. So let's say we have a point Z that is denoted with x plus iy. We want to know, this is something we have, we want to know what is P. That means we want to find out capital X, capital Y, capital Z. We want to find them out in terms of X and Y's, in terms of the information that we have. Now, the first things first, from your high school geometry, if you have a straight line like this, let's say AB, and you take a point C, you can always write it as AC by BC is equals to something, some real number, where S belongs to real number, right? And this is a positive real number, obviously, so use that plus to denote that this is a positive real number. This is the thing that we are going to use on this picture. So if you consider this straight line, we want to use this NP and PZ, this thing, okay? So how we're going to do this? Again, using NP, this segment over here and this segment over here. We want to use this, and we want to just calculate the ratios, and let's see how this whole thing works out. So this is a calculation. So this NP by what? P to some Z, right? PZ. Sorry, I think I was saying PN. Perhaps the cold issue. Okay, so PZ, and we are calling this ratio as small s. Or let's not use small s. We might get confused. So let's use let's say beta. So this is the thing. Now we can write this in terms of the coordinates as well. So we can write this as, in terms of the coordinate y, and there is this z minus 2 thing that you will see, okay? And I'm explaining why there is a minus 2 over here in a short bit. Minus 2. So why is there a minus 2, right? Because these points, that means this NP, this North Pole 002, this capital X, Y, Z, and Z, these points must lie on the straight line. And as you can see that I have said that this NP thing, right? How do you calculate NP? How do you calculate the length? So NP or PN, whatever you want to call it, is just x minus 0. I mean, this should be the length. If you consider the length, then it should be x minus 0, y minus 0, and z minus 2, but it won't be just this, it will be this thing squared and square root over this. That's the modulus of this. Okay, so we just want to have the differences right now. This is one way to think of it. So that's why there is this z minus 2 thing, and similarly that goes for this nz thing or pz thing, whatever you want to call it. And finally, if you take this thing, it will work, and you can go ahead and figure out this ratio as well. Okay, but there is a problem over here. If you consider np to pz, see what happens. Okay, I think I wrote something wrong. It shouldn't be xy, just it should be x minus capital X, y minus capital small y minus capital Y, and then there would be yeah, there is 0, so it should be minus 2, like this. And the problem would be that capital X would be equivalent to beta small x minus capital X. So this is just doing the same thing over and over again. So we can do this, or we can take the ratio of this nz and then np, or zn pn, whatever you want to call it. That would be much convenient if you consider that. So let us take that. So again, the ratios that we are interested in is just np by nz, let's call it delta, and finally you have this np is equals to delta nz. Again, this is also from high school geometry, that you have this straight line, you have this AC by BC as some real positive real number ratio. Also at the same time you have this AB by BC as, let's say, S prime, where S prime is also belongs to the positive real number and stuff. So now we write down the coordinates. So this is just capital X. So why are we writing down the coordinates? Because instead of writing down the full expression, we just want to write things in ordered pair. That makes things easier for us. And there you have a z minus 2, you have this delta, you have this capital small x, small y, that corresponds to the complex number in the extended complex plane, and finally you will have a minus 2 over here. So this tells you that capital X is equals to actually delta small x. This is one relation. Capital Y is equals to delta small y, another relation. And finally you have capital Z minus 2 is equals to delta, and there is a it's multiplied with the minus 2, like this. And our goal is to find this delta. If we find this delta, we already have this x and y's, we can find capital X and capital Y and our capital Z as well, right? So to find that, let me first put the form of Z in a more clean manner. So Z would be 2 minus 2 delta, this thing. So we are going to have to use another equation so that we can find this delta without knowing this capital Z, and that equation would be the equation of the sphere. So this is the equation of the sphere. Okay, so this would just give you z minus 1 whole square, since this is a unit sphere. So if you don't remember what is the equation of a sphere, this is just x square y square z square equals to 1. This 1 means the radius. If you have a radius r, this is r square. This is the equation of a sphere. So we use this equation, and then we have these conditions over here. So let's put these conditions over here, right? Let's try to put these conditions over here. Oh, and you might also ask, why is there is a z minus 1? Well, just look at the center. The centers are what? 0 0 on the xy plane, because the center would be somewhere over here. This is the center, and this is a what? Unit sphere. So the north pole on the z axis carries a weight of 2, so the center should carry a weight of 1, right? So that's why there is a z minus 1. And the equation that I wrote over here, this is a sphere that has a center with coordinate 0 0 0. So now let's use these conditions over here into this equation, and let's see what happens. So capital X square would translate into delta square small x square, then you have delta square small y square, and you have this z minus 1 thing, right? So z was what? 2 minus 2 delta, so there's a minus 1, so it should be 1 minus 2 delta whole square equals to 1. And if you just simplify this, this is giving you delta squared, then x squared plus y square plus 4, and these two ones, they would just cancel each other out. Minus 4 delta is equals to 0, or delta square x square plus y square plus 4 is equals to 4 delta. Now delta cannot be 0, right? Because that doesn't make any sense. And why delta not 0? Well, just look at these lines. Can the ratio of two lines be 0? No, that doesn't make any sense. So you can cancel out one of the deltas from both sides, and you have this relation delta x squared plus y squared plus 4 is equals to 4. But see, what is x squared plus y squared? This is just the modulus squared of this complex number itself, right? You have those x and y's, so this is the modulus squared, or the distance squared. So you have delta is equals to 4 divided by modulus of z squared plus 4. So we have our delta. Now we can put this delta back, and we can recover that capital X would be 4x divided by modulus of z squared plus 4. You can also keep it in terms of x and y, it really doesn't matter. Capital Y would be this delta thing, that means 4, then small y modulus of z squared plus 4, and you have the delta, so you also know the z coordinate as well. So what was z? Z was 2 minus 2 delta. You can factor this out. There is this delta, now you put the values of delta, so it would be 2 1 minus 4 modulus of z squared plus 4, and you can simplify from here. Modulus of z squared plus 4, this if you do it over here, there would be a plus 4 and a minus 4, they would cancel each other out, and you finally have modulus of 2z squared modulus of z squared plus 4, and there you have it. Through these equations you can find out the stereographic projections, that means the coordinates of the points from the complex plane to a sphere, and vice versa. Now for an infinity, that means z infinity, the point that goes to infinity, x and y, both of them goes to infinity, because the real and the imaginary part, all of them has to go to infinity. So even if you consider, let's say, y is something 0 or non-zero but finite, and x goes to infinity, you can easily show that the modulus will also go to infinity. And if you check that the coordinates x and y's, when modulus of z itself goes to infinity, these parts become pretty large, and capital X goes to 0, so does capital Y goes to 0. But what about Z? What happens when modulus of Z goes to infinity? That corresponds to the points of the point towards infinity in the complex plane. What happens to Z? We can see that capital X and capital Y, that means the points on the sphere, they go to 0, right? But it's the point of the Z coordinate that should tell us whether it lies on the north pole or the south pole, or somewhere in between north pole and south pole, because all the points over here, focus this light green line, all these points on this light green line will have coordinates of small x and small y to be 0 and 0. But how do we see that the infinite points on the infinity are mapped to the north pole? Well, take that modulus thing go to infinity and evaluate the limit. So let's try to do it. So we want to evaluate limit that goes to infinity. There is this, again this is doing a real variable calculus, because let's say this is a real thing, right? This is not a complex differentiation or complex value limit problem anymore, because this is a modulus thing, modulus squared thing in fact. So all those x and y's, they can be mapped to the polar coordinate. You can even prove it like this, that modulus of z is what? R e to the power I theta of modulus, right? And how do you calculate modulus? Well, this is just R, that's the distance. One way to think of this as this, just you take the complex conjugate and then you square root it. If you do that, you just get R, that's it. So instead of z you can also write R. So that's why I'm able to do this, because we haven't defined limits of complex variables yet. So if you take this limit right now, what would this be? Let's divide by this modulus of z squared thing. It would be 2, there would be 1, there would be 4 upon modulus of z square. Limit of modulus of z goes to infinity, that means the R goes to infinity. And when this goes to infinity, this part survives, this survives, but this goes to 0. So this is just 2. So capital Z is equals to 2 when modulus of z goes to infinity. So that's why we said earlier that the points at infinity, whatever, this one, this is mapped to the north pole. And we can also do some interesting stuffs from this stereographic projection, because if you consider a circle like this on the complex plane, this is getting mapped into the Riemann sphere as another circle, something like this. And if you consider a straight line, let's say like this, and you project all the points in this straight line into sorry, it should be like this over here, another one, let's say like this, another one, let's say like that, and all these points, they will generate a circle like this. So what is a straight line in a complex plane will be a circle on the Riemann sphere. So these are pretty interesting mappings, and hopefully we will discuss these mappings in more detailed and more rigorous manner when we study conformal mappings as well. For now, just finding out these coordinates will be enough for us. So this will be it for today, and I'll see you on the next lecture. Thank you.